Thank you, Julia, for this introduction. And hello, everybody. You will probably remember that most of my previous talks have been on environmental impacts of fossil fuel production, which is what I do most of my research on. But for this presentation, I've chosen a different title. I want to investigate potential unintended consequences of energy transitions. And the example I've chosen is biogas expansion and potential negative impact on groundwater quality. Just to set the stage, let me see how we can advance it. First issue. To set the stage, you all know that greenhouse gas concentrations in the atmosphere have markedly increased since the Industrial Revolution. And especially in the last few decades. On the top right corner, you can see a 2,000-year record of concentrations of CO2 on the top, methane in the middle, and N2O in the lower panel. And especially in the last few decades, the concentrations of these greenhouse gases have markedly increased. Isotopic data and mass balance data clearly show that the majority of recent increases of atmospheric CO2 and methane is associated with production and consumption of fossil fuels. So on the right bottom corner, you see a diagram that shows the share of fossil fuel combustion in global carbon emissions until the year 2000. And for all these reasons, transitions towards more renewable energy resources is highly desirable to reduce anthropogenic greenhouse gas emissions into the atmosphere and thereby combat the temperature increase through anthropogenic global change. Germany's Energiewende is a remarkable example of an energy transition strategy with significant contributions of renewable energy sources to power production. And on the right top corner, you see a diagram for year 2018. That is the power production in Germany and its sources. And on the right-hand side, the yellow part of that pie diagram are the renewable sources to power production, which were 35% in that year. And 7% of the power production came from biomass in 2018. But in such energy transitions, caution is required to minimize unintended detrimental consequences to other vital resources. And one of these vital resources is groundwater, which you see in the lower part. If you see my mouse, I hope, there are sandy aquifers, gravel aquifers up here, there are bedrock aquifers down here. And we have a variety of land use exercises on top of this diagram, which can potentially negatively impact groundwater through pollution. So the case I've chosen is biogas in Germany because it has seen a marked expansion, especially between the year 2004 and 2011. The diagram on the bottom shows you the number of biogas plants in Germany. So in the end of last century, there were less than 1,000 biogas plants. By 2011, there were more than 6,000 biogas plants. And now in the year 2020, Germany had more than 9,000 biogas plants, producing more than 50 terawatt hours of energy per year. So in the top right-hand corner, you see a breakdown of the contribution of energy from renewable sources. And biomass is the second most important one. It produces less energy than wind, but it produces more energy than solar energy in Germany in the year 2020. These biogas plants require feedstocks, and corn or maize is one of the key feedstocks for biogas plants. And that has a variety of different reasons. One of them is that corn grows extremely fast and has a low requirement for crop rotation. The biomass yield per hectare of agricultural land is extremely high with corn. And there's also very high yield of biogas per ton of corn used in biogas plants. So there are multiple reasons why corn is a favorite feedstock. But it requires expansion of the area of agricultural land, which is used for cultivation of these biogas feedstocks. So in Germany, there have been some conversion of grasslands to corn production, especially between the years 2004 and 2012. And currently 1/3 of Germany's corn is used for biogas production, with the other 2/3 going for animal feed. Another issue with corn is that it requires a relatively high nitrogen fertilizer input, way in excess of 120 kilograms nitrogen per hectare and year. And so that is something which needs to be kept in mind if you look at groundwater contamination with fertilizer nutrients. We'll later talk about the corn cap that has been introduced in Germany. That means that in 2018, for instance, biogas plants could only use 50% of their feedstock from corn production, and 50% had to come from other resources. So that is essentially was an incentive to increase the anaerobic digestion of manure in biogas plants, which is in full swing as I understand it. So the objective of my talk today is to assess the likelihood of potential negative impacts on groundwater quality resulting from enhanced production of feedstocks of bioenergy. And again, the example which has been chosen is corn cultivation and its potential impact on groundwater. And with groundwater, the impact I will talk about is especially nitrate contamination of groundwater for reasons which will be explained very shortly. The outline of my talk is as follows. We will first do a comparison for Alberta and Germany, look at the respective groundwaters and see what the level of groundwater contamination with nitrate is. Then we will investigate what the sources of the currently existing groundwater nitrate are. We will ask the question, how long does it take for a fertilizer nitrogen which is applied to a field to reach the groundwater, and how much of that fertilizer nitrogen reaches the groundwater. Once the nitrate gets into the groundwater, the question is how long does it stay there? So what is the residence time of nitrate? And we'll have a few slides on that. And then I have a summary and a conclusion, which wraps all of this up again in the context of sustainable energy transitions with the example of biogas. So why are we worried about nitrate in groundwater in the first place? Well, excessive nitrate in groundwater is a real health concern if that groundwater is used for drinking water purposes. The reason being, nitrate in the digestive system of humans is partially reduced to nitrite, and nitrite inhibits oxygen transport in the bloodstream. And that is especially problematic for small people, for infants. There's an issue called blue baby syndrome, which essentially means that not enough oxygen is transported, then the babies turn blue. There's also a suspected issue that nitrate is very likely to promote some cancers, although that evidence has not been conclusively come forward, but more research is done on this issue as well. For all these health reasons, there are limits of how much nitrate can be in your drinking water. Health Canada permits what's called a maximum allowable concentration, or MAC, of 10 milligrams per liter nitrate N. So these 10 milligrams are only the nitrogen in the nitrate molecule. And if you express this as a nitrate concentrations, it would be equal to 45 milligrams per liter. And in Germany, the maximum allowable concentration for nitrate in drinking water is 50 milligrams per liter nitrate. So that's very similar, but not identical to the 45 milligrams of nitrate in Canada. Another side effect of groundwater nitrate, if it infiltrates into surface water bodies, is that you get eutrophication, algae blooms. And on the right bottom slide, you see or picture, you see a eutrophication event, in Lake Winnipeg many years ago, which was quite nasty and certainly impacted the tourist industry in that area. So how many people then rely on groundwater for drinking water purposes and could be potentially impacted if fertilizer nitrogen impacts the groundwater? Well, that's quite different numbers between Alberta and Germany. Alberta has only 4.4 million inhabitants, and only 20% rely on groundwater. And that is mainly the rural population. The reason being that drinking water for people in Calgary, Edmonton, and many other larger cities comes mainly from surface water sources, but the rural population relies on groundwater for drinking water and other water needs. So that is less than 1 million people in Alberta, and the groundwater quality monitoring, which has been ongoing for a few decades, is relatively patchy, and there are not very good data sources available as we speak. In Germany, the situation quite different. In total, 84 million inhabitants. More than 70% of Germans rely on groundwater for drinking water purposes. So that would be more than 58 million people. And the groundwater monitoring has been very good for very long periods of time. So there are excellent long-term data records available to check on groundwater quality in Germany. So if we want to look at the groundwater quality in Alberta, first, this is a research project we have been involved in for over 10 years now. We have taken groundwater quality data which exists and have been collected from various agencies, including Alberta Health, Alberta Environment and Parks, and many others, amalgamated all the existing data into a unified database, did a lot of QA/QC analysis, and now have access to more than 150,000 groundwater samples. And the diagram on the right-hand side simply shows you how many groundwater samples have been obtained and analyzed in a given township throughout Alberta, which tells you that the darker blue colors, the most samples are available between Edmonton and Calgary and south of that. And in the southeast corner of the province, we have a relatively good database, which is supplemented by numerous own samples which we obtain and do analysis with. When we talk about groundwater quality, we talk about many different parameters, the major cations, the major anions, minor elements, trace elements, gases in groundwater. But what we're really interested today for the purpose of this talk is only one of the nutrients, that's nitrate, and its concentration, which is available in most data sets we have studies. So if we now look at the concentrations of groundwater nitrate in Alberta, we were quite surprised to find that in 80% of all the samples we have, there is no nitrate to be found. Nitrate is below the detection limit. So on the diagram you see on the slide, this is the average nitrate groundwater concentration per township. And you see that elevated concentrations do occur mainly in the southeast corner of the province, with the rest being below the detection limit in blue, or having no data, that would be the white areas. If you look in areas where we have elevated nitrate concentrations, it occurs predominantly in the southeast quadrant of the province. And that is the area where we have predominantly agricultural land use. The map which just showed up is showing you the manure production index. That is counting the animals which are in a township or area of land, calculating how much manure is produced and that manure is applied to the fields. And you can see that there is some good overlap between the manure applied to the fields or the fertilizers applied to the fields, which are not shown here, and the areas where the groundwater has elevated average nitrate concentrations in the province of Alberta. The next slide shows you a histogram on the left-hand side for the 20% of the samples which do have nitrate. You can see that the majority of them have relatively low nitrate concentrations, below 5 milligrams per liter nitrate N, and that there is a very small tail of high nitrate concentrations here on the right-hand side. And if you total all of this up, you will find that only 3% of the groundwater samples which are available in Alberta show nitrate concentrations above the drinking water guideline of 10 milligrams per liter nitrate in. If we now move over to Germany and do a similar comparison, we see quite different results. In Germany, there is a groundwater monitoring network with about 1,200 sampling sites. Not all of these are located within agricultural land use areas. So some of them are forested areas, grasslands, etc. And what I show on the bottom is the European Union summary of the average nitrate concentrations in groundwater in Germany starting in 1992. And the value currently is around 28 to 30 milligrams per liter. And what's important to recognize is that over these 3 decades, there is really no improvement to lower average nitrate concentrations. If anything, the nitrate concentrations are slightly increasing over the last few years in groundwater in Germany. The next insert here is from the Umweltbundesamt, and the bars you see on the bottom shows you the percentage of samples which are above the 50 milligrams per liter nitrate limit for drinking water. And so between 2008 and 2020, that value varied between 19 and 16% of all wells sampled had too much nitrate for drinking water purposes. And the blue line on top with the dots shows you what percentage of these 1,200 samples had more than 25 milligrams per liter nitrate. And again, that's more than 1/3 of the samples had very noticeable nitrate concentrations in groundwater. How is this distributed regionally in Germany? Average nitrate concentrations in groundwater are shown on the map on the right-hand side. And the legend is over here. The dark red colors would indicate that nitrate concentrations exceed the drinking water limit of 50 milligrams per liter. Orange is more than 40 milligrams per liter, and yellow and green are then lower nitrate concentrations. And you can see that certain areas in Saxony, Lower Saxony, and Schleswig-Holstein, in other words, areas with intensive agricultural land use, have high average nitrate concentrations in groundwater. The situation looks a lot worse if we do not look at average nitrate concentrations, but at maximum nitrate concentrations in groundwater per district or Landkreis. So the data you see here are for samples taken in 2015 and 2016. And reveal that high nitrate concentrations do occur almost everywhere. But keep in mind that we now look at the maximum nitrate concentrations per Landkreis in this diagram. And again, the northern areas of Germany seem to be more impacted than the southern areas. However, we need to keep in mind that the 1,200 sampling sites are not all just agricultural sampling sites. So this diagram here has subdivided sampling sites which have no agricultural land use on top of them against, and these are shown in purple, versus the data which are in green, which are for the 680 monitoring sites which are located in agricultural land. That's what the Germans call the Teilmessnetzlandwirtschaft. And if you look in only groundwater underneath agricultural areas, you will find now that the average nitrate concentrations has increased considerably to 40 milligrams per liter, that there are frequent and massive exceedances of the trigger value of 50 milligrams per liter. So all these outliers up here are 150 to 350 milligrams per liter nitrate. And the other observation is we have data from 2012 to 2016. There's really no improvement here in terms of lowering nitrate concentrations despite efforts to improve that situation. So nitrate contamination in groundwater in Germany, especially under agricultural areas, is significant. Now, the European Commission released the European Nitrate Directive back in 1991, and it requested reduction of groundwater nitrate levels for all member states to protect the water quality and have safe drinking water. It placed Germany under the obligation to prevent exceedances of a 50 milligram per liter trigger value for groundwater nitrate. And as you have seen in my previous slides, despite some efforts, the situation hasn't really improved very much in the last few years or couple of decades. And because of that, the European Commission took the German government to court in 2016 and again in 2019, claiming that Germany had done insufficient countermeasures designed to reduce groundwater loads, to reduce nitrate loads in groundwater. And because of these issues, Germany then enhanced its fertilizer ordinance or fertilizer rules in 2017, revised them again in 2020. But despite that, Germany was found guilty of not implementing the EU Nitrate Directive strictly enough by the European Court. And as you have seen, the proportion of monitoring sites which exceed the nitrate guideline remains rather constant between 16 and 19% over the last few years, with very little indication that the situation improves. So the next part of the talk, I want to just briefly spend a couple rather technical slides on how we figure out where the nitrate comes from, which we do find in the groundwater. There are various potential sources. It can be coming from atmospheric deposition. It can come from organic nitrogen in soils, which through nitrification becomes nitrate and seeps in the groundwater. It can also come from synthetic fertilizers, which are applied to the fields, or from manure, which is applied to the field, and some nitrate leaks into the groundwater. And then there are wastewater effluents from municipalities, smaller towns, or septic systems or farms, which can release nitrate into the groundwater. Now, one approach we use to figure out which of these sources provides the nitrate into the groundwater is isotopic fingerprinting. So nitrate is NO3, and it has nitrogen and oxygen in the molecule. Both of these atoms do have two stable isotopes, nitrogen 15 and nitrogen 14, as well as 18O and 16O. So we can measure these isotopic ratios. We express them in delta values, and then plot these delta values in dual isotope plots. This is one example here, which shows you the nitrogen isotope ratios on the x-axis versus the oxygen isotope ratios of the nitrate molecule. And what you now can realize is that nitrate from different sources has different isotopic compositions. So if nitrate came from rain and snow, atmospheric deposition, it would have very high 18O values and the range of nitrogen isotope values, and would be distinguishable from nitrate, which is derived from ammonium-containing fertilizers, which would have this isotopic composition down here, or soil nitrate, which would sit in this area over here, or nitrate from manure, which has elevated delta 15N values and low oxygen isotope values, again having a characteristic area in this plot, which indicates that the nitrate is manure-derived. Couple of slides to show you how we can use this tool to figure out the sources of nitrate in groundwater. This diagram is for nitrate in groundwater in Alberta. We don't have all that many samples because, as you remember, 80% of groundwater samples in Alberta have no nitrate. But here's a bunch of data from a study site in Alberta. Groundwater-derived nitrate has been analyzed for its isotopic composition, and a large number of data plot into this box over here, which tells us that this nitrate is derived from manure in Alberta, mainly cattle manure, which is applied to the fields. So especially when we have high nitrate concentrations, we often find that cattle manure is the source. There are also some samples plotting here to the left-hand side. This is soil-derived nitrate. And this nitrate is also enhanced by application of urea or ammonium-based fertilizers which then convert to nitrate and might also leak into the groundwater. So we have manure-derived nitrate, and there's some indication of fertilizer-derived or soil nitrogen, which then leaks into the groundwater in Alberta as the main sources of groundwater nitrate. Similar studies have been conducted in various places in Germany. This is just one example. I have collaborated with a colleague from the Technical University in Munich, and the diagram is of the same nature you have seen just before. These groundwater samples are from a study area near Hohentann in Landkreis Landshut, an area which has a lot of pig farming. The pig manure is applied to the fields, and lo and behold, if you take the groundwater, analyze the nitrate, the concentrations are elevated, and the isotopic compositions for many of these samples indicates that this nitrate is also manure-derived. So we have two case studies pointing us to the same key conclusion. When groundwater nitrate occurs at elevated concentrations, the nitrate is almost always derived from agricultural sources. And in many cases, we find that manure-derived nitrate occurs or shows up in the isotopic plots. And in some cases, we also see synthetic fertilizers contributing nitrate to groundwater. So after we now know what the nitrate sources are, we can start to worry about a couple of other questions. So we have so far found that agricultural activities contribute nitrate to the groundwater. That then stands to reason that expansion of the area of agricultural land needed to grow more corn, which requires a lot of extra nitrogen fertilizer, has also the potential to contribute nitrate to the pollution of groundwater. And we need to ask a couple more questions. How long does it take for fertilizer nitrogen after it is applied to reach the groundwater? And once it gets into the groundwater, how long does the nitrate in the groundwater remain there? So these are the two questions I want to explore in the next little while. How long does it take for a fertilizer nitrogen application to move through the soil zone into the subsurface, into the groundwater? This is a question we started to answer with an experiment which started a long time ago in 1982. We used what's called a Lysimeter. So this is a soil monolith, which is 2 by 2 by 2 meters, encased in an area where we can sample on a regular basis from the side and from the bottom. On the soil monolith, there was regular cultivation with sugar beets and winter wheat. So it's a regular agricultural soil, which you would find in northern France everywhere. And what we did in 1982, we applied a synthetic fertilizer at a typical rate of 120 kilograms nitrogen per hectare of year. It was a potassium nitrate fertilizer, so it's the nitrate in groundwater we're interested in. It makes sense to use potassium nitrate. And we isotopically labeled this fertilizer, as you will see in the next diagram. So this again shows you the dimension of the lysimeter. We applied the fertilizer on the top of this soil and ask the question, how much of the nitrogen is taken up by the crops? How much resides in the soils, and how much seeps in 2-meter depths towards the seepage water, which then goes into the groundwater? I mentioned we isotopically labeled this nitrogen of the fertilizer. So we used a very extreme isotopic composition of plus 10,000 per mil, completely unusual and unnatural. The baseline for plants and soils in the area is around 5 per mil. So anything which is dramatically higher than 5 per mil obviously must come from the synthetic fertilizer we applied in 1982. What we then did, we harvested the plants every year. We sampled the soils every 3 to 5 years. We sampled the seepage water continuously in 2-meter depths and asked the question, how long does it take until the last fertilizer nitrogen molecule leaves this study system? And in the meanwhile, how much of the labeled fertilizer N has been taken up by the plants? How much remains in the soils? and how much is exported towards the hydrosphere, in other words, into the groundwater. Since this is a completely closed system, we were able to account for 100% of the applied fertilizer. So what we did, we analyzed the crops and the nitrogen removal with the harvest. And I go through these diagrams fairly quickly because they are a little bit technical. So here we in 1982, before the fertilizer was applied, we would see baseline values around +5 per mil. If we didn't apply the fertilizer, but we applied the fertilizer in 82, and shortly after you see much higher nitrogen isotope ratios, which had the highest values in 83 and 84, and then decreased over the next couple of decades. But you can see that even in the year 2008, we still have elevated values above a baseline, indicating that there's still fertilizer nitrogen, which was applied in 82, hanging around in the system. We have similar results for the seepage water nitrates. So here we looked at nitrate, which percolates out of the lysimeters in 2-meter depths. Before the tracer was applied in 82, we have values around +5 per mil. After tracer application, elevated values indicating that some fertilizer nitrogen is moving through the system. But even in the year 2000, the values have not come back to the baseline. Even in the year 2008, we're still above the baseline, indicating that some fertilizer nitrogen is still lingering around. And the last slide of that nature looks at the soil nitrogen. So the total nitrogen in the soil also had elevated values a few years after tracer application. And then a couple of decades later, we still see that the soil nitrogen has some of its tracer in it because the values have not come back down to the baseline value of +5. So we can now take all these tracer data and put them into a mass balance and figure out what has happened to the 100% of the fertilizer nitrogen we have applied in 1982. And we only do this for the first year, 5 years here. So after 5 years, about 50% of the fertilizer has ended up in the crops. Most of it in the first year with the first harvest, but in consecutive year, a little bit of fertilizer nitrogen still went into the crops in year 2, 3, and 4. In the soils, after 5 years, we still had 27 to 35% of the fertilizer nitrogen. And in the leaching with the seepage water in 2-meter depths, we had small contributions, but significant contributions, less than 5%, but measurable amounts of the fertilizer leaching towards the groundwater. We continued this experiment for about 3 decades. And here you see the entire mass balance after 30 years. We just mentioned that initially 50% of the fertilizer ended up in the plants. In the next few decades, that value increased ever so slightly to close to 60%. The soil organic matter pool was about 25 to 35% 5 years after tracer application, and then decreased over the years, but did not go back to baseline values. Why did it decrease? Because some of that nitrate leached with the seepage water towards the groundwater. So after 30 years, 14 to 19% of the fertilizer nitrogen was still in the soils. And after 30 years, approximately 10% of the fertilizer which was applied has left the lysimeters and leached towards the groundwater in form of nitrate, causing nitrate contamination in the aquifers. So you can see that the soil organic matter retains a lot of that fertilizer nitrogen. And that enabled us then to do a very simple model, an exponential fit to the soil nitrogen delta 15N values, which were still elevated in the year 2008. And we asked us how long would it take until these values would decrease to the baseline value of +5 per mil. And if you look at these exponential models, you see that by the year 2080 to 2090, the last molecule of fertilizer nitrogen, which was applied in 1982, will have left the soil system. In other words, this is a 100-year turnaround. And in these 100 years, between 12 and 17% of fertilizer nitrogen which is applied will be lost to the groundwater and contaminate the hydrosphere at decadal timescales, at very slow timescales. So it takes a long time for the fertilizer nitrogen to go through the soils and reach the groundwater and cause the contamination. Now, as this groundwater then migrates away from a recharge zone through the aquifer, there's a very typical redox sequence which occurs. In groundwater, we typically have a lot of oxygen initially, but this oxygen is consumed slowly, so the oxygen decreases. And as we go in more reducing conditions, when oxygen is reduced, nitrate can be denitrified. And I bring this redox lead up because this is the key process which can remove nitrate from groundwater. Microbial activity converts nitrate into harmless N2, and the nitrate disappears. But that is only possible after all oxygen is consumed in the aquifer, and that might take some time. So we'll have a look in this diagram. We go back to the study I mentioned before with the colleagues from the Technical University of Munich, where we looked into an aquifer and groundwater system, which is nitrate contaminated near Landshut. And this diagram shows you how much oxygen is in the groundwater on the left-hand side. And on the x-axis, you see the mean transit time of the groundwater, how old the groundwater is. And all I want you to see here is that the younger groundwater, which is 10 to 20 years old, has still very high oxygen concentrations. And that means that denitrification, the process which removes the nitrate from the groundwater, cannot occur. Denitrification requires oxygen concentrations as low as this dashed line down here. And you can see that there's only one sample or a couple samples which have low enough oxygen concentrations that nitrate removal through denitrification can occur. But this typically happens with the older groundwaters, which are 30 to 100 years old. So as long as the soft oxygen concentrations remain high, nitrate is very persistent in the groundwater and will not be denitrified and can remain in the groundwater for hundreds of years if the groundwater residence time is long enough. In Alberta, we have much more reducing groundwater for various reasons. A lot of our groundwater is in the sulfidic and methanic area down here. And that is the reason why 80% of Alberta's groundwater samples do not contain nitrate. It doesn't mean that there was never nitrate in the groundwater in the first place, but the groundwater is reducing enough that this nitrate is converted to a harmless N2 gas. And that is the reason why nitrate doesn't occur frequently in the groundwater of Alberta. So now I want to bring this back to sustainable development of renewable energy resources. If we summarize what we learned so far, elevated nitrate in groundwater is mainly derived from agricultural activities, expansion of corn growing with high nitrogen fertilizer requirements will make this issue more problematic as we go forward. For how many people is this problematic? Well, in Alberta, less than 1 million people are affected by using groundwater. In Germany, it's more than 58 million people. The percentage of groundwater samples which have no nitrate in it in Alberta is 80%. In Germany, I couldn't find a definitive number, but it's very few samples which have absolutely no nitrate in it. The percentage of groundwater samples in Alberta which are above the drinking water guideline for nitrate is only 3%, whereas in Germany it varies between 16 and 19%. And the potential for nitrate removal through this denitrification process is very high in Alberta because we have highly reducing groundwaters, whereas in quaternary gravel aquifers in Germany, often the dissolved oxygen is so high that denitrification cannot commence. So the conclusion of all of this is that expanded corn cultivation requires high nitrogen fertilizer inputs and has significant potential to further contribute to groundwater contamination with nitrate. The timelines for fertilizer-derived nitrate transport into groundwater and the nitrate residence times in aquifers can be often of the order of decades, and that has been previously overlooked. So when the EU introduced its nitrate directive, it assumed if action is taken within a few years, you would see a positive impact. But if it takes 2 or 4 or 8 decades for the fertilizer nitrogen to move into the groundwater, then we see the groundwater contaminated today with nitrate, which has been applied in the 60s and the 70s, and the big ticking time bomb of the additional nitrogen which has been added in the meanwhile is still to come. And if nitrate is in the groundwater and the groundwater is not reducing enough, it might stay there for another few decades. So very quick action is very difficult to achieve in systems which have such a long transit time. Because of that, careful management of the feedstock mix for biogas production is desirable if a sustainable growth of the sector is desired. And this corn cap, which I mentioned before, is one of the most effective measures which have already been introduced. I've mentioned that in the year 2018, only 50% of the feedstock which goes into biogas plants can be from corn production. In the meanwhile, this value has been brought down to 44 or 42%. In the realization that groundwater quality need to be maintained and excessive extra growth of corn for biomass gas plants with fertilizer inputs might not help to bring the nitrate concentrations in groundwater down. With the few acknowledgements of the funding agencies which have helped us to do some of this research in Alberta, I want to thank you for your attention, and I'm happy to answer any questions you may have. Thanks.